Okay, welcome to week 2, lesson 1 on oxidative addition, the first reaction type that we'll study in organometallic chemistry. There are two main types of this chemical reaction, those that involve non-electrophilic substrates. These are non-polar substrates such as methane or silanes or dihydrogen. They also include electrophilic substrates such as methyl iodide or methyl triflate. We are going to study these chemical reactions using the CBC classification method and by using the oxidation state, or what we've been calling the valence number and the valence electron count, the DN count, and the coordination number, or the ligand bond number. We will be able to classify these reactions. Reductive elimination is the microscopic reverse of oxidative addition, or oxidative addition's tricky friend, and it also has two types, either electrophilic or non-electrophilic, depending on the substrate, and we will be classifying these reactions according to the terminology we've developed in class so far this semester. I have discouraged you from doing arrow pushing in my class so far, but this is one case where it actually works pretty well. You just have to remember that the lone pairs in transition metal compounds are not stereochemically active and they don't take up space. But if we do the arrow pushing in this reaction, we see that this lone pair will push off the iodide, making a free iodide and forming the metal carbon bond. So here's our metal carbon bond. The free iodide was in solution and will coordinate to the metal, resulting in the final metal iodine bond. Here's an example of a real chemical reaction. This is platinum DPPE dimethyl. So DPPE is a bidentate phosphine that has two phenyl rings on each phosphorus, and there's an ethylene linker, so DPPE. This reacts with iodomethane, and they've deuterated the iodomethane as a label in order to track the chemical reaction. So what we can see is, in the first step, this is an intermediate, we have the CD3 group attached to the platinum, and then in the second step we form the platinum iodide bond. This labeling study was done for NMR purposes rather than IR purposes. The CD3 group would not show up in a proton NMR spectrum, and you would be able to see the progress of the chemical reaction. So this is the example of the mechanism using a polar substrate, or a substrate that undergoes an SN2 type of a reaction. The next slide shows the reaction using a nonpolar substrate. Nonpolar substrates have a pretty different mechanism. This is A prime, which is meant to indicate that A and A prime are approximately the same element. They have similar electronegativities. And rather than going through an intermediate like in the previous case, this is a transition state where we have begun to activate the AA bond and begun to form the MA and MA prime bonds at the transition state. The product then results in the metal A and A prime bonds being formed. Here's a real example. This is called Wilkinson's catalyst rhodium tris triphenylphosphine chloride. Reacts with dihydrogen to form this transition state with this cyclopropane-like ring. Both hydrogens are being activated, the HH bond is being broken, and the final product has a cis arrangement. So an important take-home message here is nonpolar substrates result in a cis arrangement, and that's because of this transition state where the two incoming ligands are right next to each other. The polar substrates, which we'll usually see as methyl iodide or methyl triflate, end up trans to one another because you form the bond and then the leaving group swims around and finds the other side of the metal complex and binds trans. Okay, so we can classify these reactions and use that classification to help determine whether or not the reaction is an oxidative addition or a reductive elimination. So classify these three complexes. We have the palladium tris triphenylphosphine, we have the palladium tris tris-triphenylphosphine methyl cation, and the final product, palladium tris-triphenylphosphine methyl iodide. So assign these the CBC number, the valence number, ligand bond number, metal DN count, and valence electron count. Do this on your own, and then I'll post the answers after a few seconds. Okay, hopefully you got these answers. If you didn't, review this, make sure you can figure it out. Let's see what happened when we did this chemical reaction. First of all, this chemical reaction takes place in 2 steps. Addition of the methyl group to give this intermediate, and then the final product is the methyl iodide complex. We're starting with a palladium L3 complex that, since the metal has no X ligands, the valence number is 0, the ligand bond number is 3, the DN count is D10, palladium is in group 10 of the periodic table, and there are no X ligands, so all 10 of those electrons come to the complex, and the valence electron count is 10 plus 3 L ligands, giving 16. I'm not going to go through the rest, you can check your work, but let's look at what happens to this chemical reaction to all of the counts. First of all, the valence number starts at 0 and goes to 2. We've oxidized the metal by 2. The ligand bond number starts at 3 and goes to 5. We've done an addition of 2 ligands, hence the name of the reaction, oxidative addition. The DN count drops by 2. The valence electron count goes up by 2. So these 4 metrics will allow you to classify a reaction as an oxidative addition. Now try to classify this chemical reaction. First of all, calculate the CBC, VN, LBN, DN count, and valence electron count for complexes A, palladium DPPM PHH, phenyl hydride, and palladium DPPM. Hopefully you got these numbers or can figure out where these numbers came from. The valence number is dropping from 2 to 0. The ligand bond number is dropping from 4 to 2. The metal DN count is increasing from 8 to 10. The valence electron count drops from 16 to 14. These changes are indicative of a reductive elimination, and we can see that we have reduced the palladium from +2 to 0, a reductive, and we have eliminated benzene. We formed a carbon-hydrogen bond, and that's an elimination, so it's a reductive elimination. This table is explained in the chapter, so I'm not going to go over it in a lot of detail, but I want to highlight a few things. So since an oxidative addition requires oxidation to proceed, you might think that increasing electron density at the metal center would cause an increase in the rate or the favorability of the reaction. So looking at the reaction of iridium X carbonyl bis triphenylphosphine, where X is either chloride, bromide, or iodide, doing the nonpolar oxidative addition with H2 or with O2, what we see is chloride is more electron withdrawing, and there's less electrons on the metal. Iodide, there's more electrons on the metal. The more electrons on the metal gives us a higher rate constant, a faster chemical reaction. The same thing is observed in this portion of the table. The other thing I want to point out is the delta H and delta S of activation. When we talked about the Eyring equation, we talked about delta H being less meaningful. Let's look at delta S of activation here. We see strong, high, negative numbers for delta S of activation, which is extremely suggestive of a transition state where 2 molecules are coming together to form 1 molecule, negative entropy of activation. This bottom example, which is a addition of methyl iodide, so a polar 2-step addition process, we don't see the same trend. We see a slight decrease, not nearly as dramatic as the increasing in the previous examples, in the rate, but it's opposite. Chloride is faster than bromide, which is faster than iodide. And the authors of the study suggested that there were some sterics going on trying to bring that bulky iodide group close to the metal center. That brings me back to my favorite quote from Chuck Casey: "The complex web of kinetic and thermodynamic factors is further tangled by the subtle interplay of sterics and electronics." And unfortunately, we try as hard as we can to make good trends and figure out trends in these reactions, and sometimes we have to wave our hands and say we don't know the answer yet. Let's have a growth mindset. We're still finding wrinkles in this. Although generally accepted that electron-rich metal centers will do oxidative addition more favorably, this paper from 2016 shows that less electron-donating ligands strongly favored oxidative addition in one particular class of compounds. So the broader the claim you're trying to make, the less likely it's going to be valid across in detail. Is this an oxidative addition reaction? So I'm not going to put the answers in this PowerPoint, in this movie. I will put the answers on Sakai. Do the work, see if you can classify it, and tell me whether or not this is an oxidative addition reaction. And you can check your work later or talk to me in office hours this week. Your first collected homework this week is going to be draw an oxidative addition mechanism. So you can post that answer on Sakai. Try to do it without looking back at the notes. Try to make sure that's cemented into your brain. The second homework assignment this week is going to be looking at a paper by Karen Goldberg, which is one of my favorite papers, and this is a figure from that paper. And what she did is she studied the reductive elimination of two substrates in one. So we have an iodide and 3 methyl groups, and so you can have reductive elimination of ethane, so to give this product, or you can have reductive elimination of methyl iodide to give this product. And the very careful work that was done in this study still holds true today for the most part. So that'll be your second homework assignment. The next video will be insertion and elimination. And remember, please do the homework, the guided inquiry on the insertion reaction before watching the next video.